Hello, Math Humans. We're going to do 3.5a today. We're going to be talking about limits at infinity. Our objectives are that we are going to determine the limits as f of x approaches infinity, positive or negative, and then we're going to review horizontal asymptotes. So I've pre-written a few things. Remember that end behavior is what happens at the extreme ends of the graph. And we've talked about that now for a couple of math courses. So now I want to review the rules for horizontal asymptotes. So if I have a rational function, which is a function divided by a function, if the degree of the denominator is higher than the degree of the numerator, then the horizontal asymptote would be y is equal to 0. So an example would be, let's say I have x squared plus 2x, and then I'm going to divide by x cubed, then the horizontal asymptote would be y is equal to 0. Remember, for asymptotes, you always need to tell me what type of asymptote it is, horizontal or vertical, and it's always an equation. Okay? If, on the other hand, the degree is the same in the numerator and the denominator, then the horizontal asymptote is just the quotient of the leading coefficients. So let's say I had y is equal to 2x squared plus 3x, and I would divide by 5x squared plus 7. Notice that the degree is the same, top and bottom, and so then I would report that my horizontal asymptote is going to be 2/5. Okay? And then the last situation would be if the degree in the numerator is higher than the degree in the denominator, there is no horizontal asymptote, but there is a slant asymptote, and you have to do long division to find the asymptote. Your slant asymptote then is going to be the quotient. So let's say if I had y is equal to x squared plus 8 divided by x minus 7, okay, I would know that I have a vertical asymptote, but I'm also going to have a slant asymptote, right? And so I would divide x minus 7 into the x squared plus 8, right? And then the quotient would be your slant asymptote. All right, so if we want to talk about asymptotes from a calculus perspective, we talk about it from as limits. So for the calculus, let me scoot it up so you can see, the calculus version of a horizontal asymptote would be that the line y is equal to L is a horizontal asymptote if the limit of the function as x approaches, sorry, you can't see that, that's a bummer. Now you can. Plus or minus infinity is going to be L. So that's just the way that we talk about our horizontal asymptotes from a calculus perspective. All right, let's do our first example. So example number 1, and it's going to say find, that's a D, the limit as x approaches infinity of 2x minus 1 over x plus 1. Now, there's lots of different ways you can do this, but if you'll notice the degree is the same, top and bottom, my leading coefficients are those guys, the limit is just going to be the horizontal asymptote, and so I would say that the limit of f of x as x approaches infinity is going to be 2. All right? It's really pretty easy. You always want to look for the horizontal asymptotes because it makes your life significantly easier. All right, so before we do our next example, I want to consider the problem, the limit as x approaches infinity of 1 over x, and the graph of that looks like this, right? So it's just your standard function. But in general, a function is going to approach the horizontal asymptote. In this case, it would be y is equal to 0. And so it's creating a tool that we can use in other situations. So typically, if I had a complex function, but I could look at individual pieces of that function, then I would know that that portion of the function is going to go to 0. This is the notation, so I would show that it's going to approach 0. Okay? So let's look at our last example again. So if I want to have the limit as x approaches infinity of 2x minus 1 over x plus 1, if I tried to do substitution or direct substitution, I would get that this is the indeterminate form. And remember that the indeterminate form could be 0 divided by 0, infinity divided by infinity, or a combination of those. So sometimes what we do is we try to manage a limit algebraically. So let me show you how that would work. So if I have the limit as x approaches infinity, I'm going to divide each term by the highest degreed term. And in this case, the highest degree is x. So I would have 2x minus 1 over x, and then I would have x plus 1 over x. So then I'm going to split this up, the limit as x approaches infinity, and I would have 2x over x minus 1 over x over x plus 1 over x. And so all I did is split each term up. Well, remember we talked about this special situation. So now I know that as x approaches infinity, this guy's going to go to 0, this guy's going to go to 0, this guy goes to 1, this guy goes to 2, so the limit would be 2 over 1, which is 2. So if you are asked to do the problem analytically, that would be your approach to eliminate the indeterminate form. And it's not the only approach, but it is an approach. Okay? So let's do another example of a problem analytically. Okay? So this is going to be example number 2. And it says find the limit using horizontal asymptote rules and keyword analytically, because we always want to make sure that we can solve a problem both ways. The problem is going to be the limit as x approaches infinity of 2x plus 5 over 3x squared plus 1. Well, if I do it using horizontal asymptotes, I notice that the degree is higher in the denominator, so my horizontal asymptote is y equals 0. Therefore, the limit as x approaches infinity of 2x plus 5 over 3x squared plus 1 is going to equal 0. Okay? And you could confirm this graphically. You could put the equations in your grapher and look. Now I want to do it analytically. So if I look at my function, I notice that x squared is the highest degree, so I'm going to divide, and remember we have to carry the notation through until we can do our direct substitution, every term by the highest degreed term. And if you'll think about this also, I'm not changing the value of the equation, I'm introducing 1, it just happens to be a special 1. So then this is going to be the limit as x approaches infinity of 2x over x squared plus 5 over x squared, and then I'm going to have 3x squared over x squared and 1 over x squared. So now if I look at each of the individual terms, the degree is higher, it goes to 0. The degree is higher, it goes to 0. The degree is higher, it goes to 0. And this guy is going to go to 3, so it's going to be 0 divided by 3, which is 0. And then I have to write my conclusion statement at the end, so the limit as x approaches infinity of the function is equal to 0. When you do these problems, I need to be able to follow your work. If you were taking the AP exam, your AP reader would need to be able to follow your work. Therefore, you have to make sure that you, A, show all steps, that you carry the limit notation throughout the problem, and that you make a limit statement at the end. All right, for our next example, example number 3, it says find the limit, same directions, utilizing horizontal asymptote rules, and analytically. All right, so problem's going to be the limit as x approaches infinity of 2x squared plus 5 over 3x squared plus 1. So it's the same basic problem, but before I do any math, I notice that the horizontal asymptote, the degree is the same, top and bottom. Therefore, my horizontal asymptote is 2/3. Therefore, the limit as x approaches infinity of 2x squared plus 5 over 3x squared plus 1 is equal to 2/3. Super simple. Oftentimes on a multiple choice test for on your AP exam, these guys will show up in the no calculator portion of your test. Super simple, because then it's multiple choice. I'm always going to look for that horizontal asymptote. If I do it analytically, so here's the limit as x approaches infinity, 2x squared plus 5, and I'm just going to go ahead, my highest degree is x squared, just to save a little bit of writing time, plus 1 over x squared. You do have to show that you split each of the elements up into separate terms. So this is 2x squared over x squared plus 5 over x squared over 3x squared over x squared and 1 over x squared. The reason that I would do this is because I have the indeterminate form. I would get infinity over infinity. So now I notice that this guy goes to 0, this guy's going to go to 2, this one goes to 0, and this one is going to go to 3. So my limit is 2/3, and then I write the limit as x approaches infinity of f of x is equal to 2/3. Now, if you wonder why I did this differently, no special reason. It just is notation. So I chose to do this on the second one. Okay. So example number 4 is going to say find the limit. Then I'm not going to tell you how, and I'm going to have the limit of 2x cubed plus 5 over 3x squared plus 1 as x approaches infinity. So since it wasn't told that I have to do it analytically, I'm going to do this one using my asymptotes. Notice that the degree is higher in the numerator. So I could do long division. So 3x squared plus 1, and I'm going to divide it into 2x cubed plus 5. And so I'm going to get 2/3 x, right? And I'm going to stop. I'm not going to do the rest of the division because this is primarily what I'm going to look for. I know that I have a slant asymptote, and it's going to be y is equal to 2/3 x. When I get down here, I do not have any vertical asymptotes because this would be an imaginary number. And so if you think about it, y is equal to 2/3 x means that my slope of the asymptote is going to look like that. And regardless of where the curves are, maybe the curves are here and here, I don't know, I would have to put it in my calculator to determine. But notice that the function as x approaches infinity is going to approach infinity. And we've talked about this before. Technically, we could write that the limit is infinity, but because it's an unbounded, it increases without bound, the limit doesn't exist. So I would write the limit as x approaches infinity of f of x is equal to infinity, therefore the limit does not exist. Okay? So this acknowledges that you know where the function or what it's approaching. This acknowledges that the limit technically doesn't exist because the function would increase without bound. All right, we have one more example to do, and then we're done for the day. All right, so example number 5 says find the limit as x approaches infinity of 3x minus 2 over 2x squared plus 1. Now, I have no idea what that graph looks like, but I'm telling you, we're still really primarily interested in the leading coefficients of the leading variables. So this would be basically like 3x divided by the square root of 2x. Notice that the degree is the same, top and bottom, because I took the square root of the first term. Nobody cares about that little guy, right? Not for right now. So then that means that my horizontal asymptote is going to be 3 over radical 2. So then I would write the limit of f of x as x approaches infinity is going to be 3 over radical 2. And as long as all of your work is apparent, they will know how you got to that answer. So always make sure that you're looking at your leading terms, and if it says to take the square root, just take the square root. That wasn't so bad. All right, my dears, that is it for today. I will see you soon.